Assignment 2. Write a recursive algorithm to implement the Tower of Hanoi. First step is the algorithm and the pseudocode, which is here. You can see that the main part of this recursive function is this function I call solve here. It takes three parameters as input: the origin pack with all disks in descending radius with number of disks given by a positive integer n, with destination pack and help pack both are empty. The output of this is with origin pack and help pack empty, but the destination pack have all n disks in descending radius. So first we define the base case. If the length of destination pack is not 0 and the top of destination pack is larger than the top of origin pack, in this case we cannot move, just return. Else, if the length of origin pack is 1, that means it's at its final stage, so we just move this disk from origin pack to the destination pack and then return. Or else, we make a subpack which contains all the disks except the bottom one from origin pack, and then we do a recursive call of this function to move this subpack to the help pack, so that later we can move the bottom disk from the origin pack to the destination pack. So after we did that, now we want to move the disks from help pack to the destination pack, but we want to make a sub help pack which contains all the disks that are smaller than the top of the destination pack. And here we do another recursive call to move the sub help pack to the destination pack. The reason we make a sub help pack here is because if we use all the disks in the help pack, sometimes there might be more, and with some disks that is larger than the top of destination pack. And if we contain those disks, then the disk to move to which location, it might go wrong if we don't remove it. Second part is analysis of runtime, which is here. So we can see that within each recursion, it makes two sub-recursion calls. If we let t of n denotes the time of moving n disks from origin to destination, then tn comprises of these three parts below. It contains to move the n-1 disks from origin to help. It contains to move one disk from origin to destination, and it contains to move n-1 disk from help to destination. So we can clearly see that t of n equals to 2 times t of n-1, plus 1 is the movement of one disk from origin to destination, plus c are some constant operations within one function call. And we will just simply note it as plus c. We don't write plus 1 here anymore in the later process. This is a geometric sequence with common ratio of 2. So if t of n equals to 2 multiply t of n-1 plus c, then so on and so forth, we can see that it equals to 2 to the n-1 power multiply t of 1 plus c minus c. So we can clearly see here t of n is big O of 2 to the nth power, which is exponential. Next, I'm going to explain how the implementation by Python works for this Tower of Hanoi. So first, I define a class of Hanoi. Within this class, I define a non-public class for the pack stack. This is a stack that is easily defined by the list, but we make it a class so that the functions of list will not be directly called, because we make a internal variable to record the list. So with that, we only define a function of what a stack have, like it's empty and push, top, pop. Also, we define a function to get the string for display. This is just for showing how the execution went later. With that, we start to define the initialized of this class Hanoi. It should be given a parameter of n, which represents the number of disks initiated. N has to be a positive integer, so we check whether it is integer or whether it is positive. If not, we'll raise an error. And next, we initialize the 3 pack, and we put the n disks into pack A. Because stack is a first in, first out structure, so when we push it in, we have to make sure to push the large number in first and then push the smaller number later. So here we have to make it reverse order to push it in. And we use the internal variable count move to count how many movements that it makes. We use the internal value of n to record the number of disks that it initialized. we make a print current status internal function to print the current status of all 3 packs. Here comes to the main function of the move process. It is basically described in the algorithm pseudocode earlier, but it's just the implementation. So here, first part is check whether destination pack have disks and check whether the top of origin is larger than the top of destination. If so, cannot move and just return. Else, the base case is to check whether the length of origin is just 1. If so, there's only 1 disk. We just move it and then return. Or else, we go to make a subpack for the origin pack, which contains n-1 disks from the origin. And we use a list to contain the elements popped from origin pack first, because if we just push it directly from the popped value, then it is reverse order, which we don't want. So therefore, we use the temp list to record it first and then to reverse it and push it into the subpack. And this is the recursive call to move the subpack to the help pack, so that later in this step, we can move the bottom disk from origin pack to the destination pack. For the next step is that we want to move the disks from help pack to the destination pack. And first we check if there is any element from help pack to be moved. If so, we check if the length of destination pack is 0. If so, we just move the help pack directly to the destination pack. Otherwise, we have to create a sub-help pack to record all the disks that's smaller than the top of destination pack. And then we make the recursive call and move the sub-help pack to the destination pack, and it is done. We use a solve function to call this main move function, but also like print some execution things to show how this went for this process. And we also make the test of seeing, given the number of disks from 4 to 7, what would the result be like? And let's see how the execution goes. Okay, so we can see that Hanoi Tower before moving, where pack A holds all the elements, and after moving, pack C holds all the elements. This is 4 disks, and in total, it needs 15 movement. For 5 disks, it's similar moving, and it needs 31 movement. And for 6 disks, it needs 63 movement. For 7 disks, it needs 127 movement. We can also see that each of the number later is equals to 2 times of the movement before plus 1, which is consistent to our analysis of runtime before. This is for my assignment 2.